Yep. So my name is Sasha, and today we'll be talking instead of Andy. And the topic of our today's lecture will be so-called gravitational memory. Yes, feel free to stop me and ask any questions, of course. And memory here refers to memory as we usually understand it, something that stays after things have passed or gone or over. And gravitational stands for the fact that we'll be talking about gravitational field. And in a nutshell, we will be talking about certain effect of gravity waves on detectors. So the subject is very old and similar to the stories that you've heard about BMS symmetry and the soft theorems, which come from many years ago. The notion of gravitational memory also is quite old, but recently it got some new attention, I guess, in light of all these developments by a group here. And let me start, since we will be talking about gravity waves, a short review of just sketch of important dates, I guess, in the history of gravity waves. Just 1 minute, which is that in 1916, Einstein wrote his paper about gravitational waves, where he corrected some mistakes of his previous paper, and he derived quadruple formula, famous one. Then in 1936, he and Rosen famously submitted a paper where they questioned that the gravity waves exist, and then famously Einstein complained, well, that back then, if I understand correctly, it was not usual that papers were refereed, and so the paper was rejected, that gravity waves do not exist. And in his complaint letter that he sent to the editor, he said, "I send you my paper to publish, not to referee." So these days so then the next date, I guess, is 1975. It's a famous result by Hulse and Taylor, where they observe a binary pulsar. So you have a star and another star, and it emits, say, electromagnetic waves. So you observe them. And then, due to the Doppler effect, when it goes away from you or comes back, the frequency is slightly different. And then you can use Einstein quadruple formula to predict, since the system radiates energy through gravity waves very efficiently, you predict that the orbit will change. And then this system is observed since 1975. And if you look at the plot, it agrees perfectly, the change of the orbital period due to gravity waves. So this is indirect observations of gravity waves, and they got Nobel Prize in 1993. And of course, in 2016, so this year, there is this direct observation of gravity waves by LIGO and Virgo, and you probably all seen this plot where, well, from coalescence of black holes, where the plot that you've seen, I guess, to me it looks something like this. You have nothing, then you have an intense phase, and then nothing. So, and this is called strain, and this is time. So how do you detect gravity waves, and what will be a detector in this talk? I will also talk a little bit maybe about electromagnetic memory. Well, so detector will be some body with some structure, a couple of bodies with some simple structure on top of them. For example, in the case of gravity waves, you can imagine, say, two bodies moving on some world lines. And these world lines can be geodesics, but not necessarily. And each of these observers, well, this observer, let me call it observer, it can carry a clock, for example, or something else. But in the simplest case, it carries a clock, and then they can exchange signals, light signals. Say this observer and this observer, and let's say when they synchronize the clocks and they put stamps when you receive the signal and send it back, and then by doing this simple procedure, first they synchronize the clocks, then some wave comes or something happens in the space-time, and they check their clocks at distance between them by exchanging signals again, and then they can conclude if their clocks are still synchronized or not. And the effect of gravity waves is, well, will be that the distance between this the distance between these bodies will be changing, and generically also the time, well, so the time clocks will get desynchronized. The simplest way to see it is to consider, say, a plane wave. Say, well, this will be a linear approximation if you consider the metric of this form. Which is just a, say, flat space, of course, and u and v are t plus minus x3. Then you can add to it some function of retarded time. And you can check that to first, this is a function of retarded time. And you can check that this satisfies vacuum Einstein equations. So this function is a complex function. That's a complex conjugate. So it has 2 degrees of freedom. These 2 degrees of freedom are helicity of 2 gravitons, helicity plus and helicity minus. And well, the dependence on u is the profile of the wave. So that's this plot. Now you can check also in this space-time that if you consider a particle at constant z and z bar, so z bar constant, it's a geodesic, and of course then you can immediately see that if you have a fixed separation between particles and the delta, so if you have 2 particles separated by delta z and delta z bar, as gravity wave arrives, the distance starts changing because of these terms. When h is 0, the distance is just product, and then when gravity wave arrives, then the distance changes. Now you can ask the following question. Well, this plot has a particular feature which you can ask why is it true, and this feature is the following. Imagine I plot instead of this figure something of this sort, where there is a residual h of u plus infinity, we call h final, which is non-zero. Could it be? Could it be the case? And well, first of all, maybe if you can remember the simple fact that energy, well, in this simple model, energy carried by gravity waves is given by h dot square, and so this omega. Well, that okay. Sorry. Let me. If you consider space-time with with a constant h, let's say this h depends on you can make a simple diffeomorphism, which is of this type. Z goes to Z minus H final Z bar going to Z minus H final Z. And then this is just becomes a flat space. So this is a flat space. And of course, if this is a flat space, you don't need to have a source. There are no gravity waves. There is nothing. So in principle, you can think, well, there should be some residual profile of the sort. And well, what is the physical meaning of this residual profile? Well, the physical meaning is, as I explained, you have two bodies. They move on their, say, geodesics in this case. And the gravity wave comes, and they start to oscillate. And then the gravity wave passes away. And the distance between the detectors has changed. So there is a residual deformation of the detector, and this effect is called gravitational memory. It was first, well, as far as I know, again, it was first discussed around, say, 1974, maybe 73. Say, well, there is one paper which talks about it quite explicitly. Is a paper by Zeldovich and Polnareff. And they study gravity waves from super dense cluster of stars. That's how the paper is called. But they noticed that generically, if you have a gravitational wave, then there is the shape is not of this sort, but of this sort. And actually, if you look at this paper of this year, which appeared. And which will get probably a Nobel Prize soon, is that the profiles that you see, the actual physical waves that you expect, as I'll try to explain, is of that sort. But because the detector, so the way LIGO works is notice that you have these two bodies, and here they were falling freely. But if they are attached to something like a mirrors, there is a frequency range in which the detector is sensitive, and say for LIGO it's around 100 hertz. And this effect is zero. It's an infrared effect. It's at zero frequency. Well, it's a low frequency effect, and they just cannot see it. But the signal itself that was produced in the merger should have this memory. And there are, well, I'm not expert, but there are efforts to detect these gravity waves. Using this, detect this gravitational memory effect using some other experiments. Say, LISA space experiment, when there are satellites which are freely flying in space, is better for this kind of effect. Well, notice that let's to connect maybe with something that you remember from previous lectures, let us do the Fourier transform of this signal and see how does this signal look in Fourier space. So, well, the simplest way to model this the signal is to consider h of u being a theta function. And as you might know, that if you consider the signal and you do Fourier transform of it, you will get that h of omega is has 1 over omega pole. So in Fourier space, this corresponds to 1 over omega tail of the gravitational field. And this will be important when we will try to connect this to the soft theorems, etc., etc., etc. Now, in principle, you can immediately think, okay, what does this memory do? So we compute the, well, let me rewrite this delta H in some way that, let's say, we wait for a long time. And you have integral of this sort, du of H, it's a total derivative. And you see, if you compute it, it computes H of plus infinity minus H of minus infinity. And this is exactly the memory. So, and this corresponds to this usual gravitational memory. And it corresponds to 1 over omega term in the expansion. Now you can consider some higher moments of this sort, which will, in principle, you can imagine immediately writing the integral of this sort, u minus u naught to the n du to the h. Well, you can show that this is trivial to see, that this will correspond to probing next terms in the 1 over in the soft expansion. So for n equal 1, it will be h. So we will have h of omega is equal m0 omega plus m1 plus m2 omega. So these soft factors are related to this kind of higher moments of the metric, if you wish. And well, but the unpleasant thing about these moments is that there is this arbitrary parameter u naught, and you see that, well, depending on how you choose u naught, you can shift higher moments by lower moments. Well, anyway, that's maybe not so important, but there is this, so you can consider these moments. As soon as you realize that the first moment is given gravitational memory, you can define these new memories, and you see that this kind of new memories are related to this expansion of the amplitude. But of course, the unpleasant thing about these moments compared to that one is that this integral is really localized at the boundaries. You can compute only, you can know only the metric far in the future and far in the past, whereas for these moments to compute the integral, you really have to integrate over time. So they're a little bit non-local. That's unpleasant, and they're not really memories in this sense. So, okay, if we see that generically we can have this this effect, what the question you can ask? What kind of sources produce this effect? And well, the answer will be generic, but it's useful to consider something, some simple source, and the simple source that you can consider is the following. And so now I'm thinking about solving. So gravity waves are sourced by matter, of course, and so we have G nu equal to And let me choose T menu to be the following configuration. We have a set of now, say, set of particles, which with some momenta, P1 initial, Pk, and say P final, Pk, such that sum of a initial and equals sum of a final. And the stress tensor of a particle is just say, will be integral over the proper time, for momentum, and for velocity and delta function in 4 dimensions, x minus x mu of tau. So this stress tensor is localized at the location of the particle, and it has this this form. Now you can plug this simple model into the equation. Well, in this simplest in the gauge where the equation takes a form again. And then you can use a simple retarded propagator and solve for the h, and you find something something quite interesting. Is that, well, if you take as a retarded propagator, compute h mu using it. And then takes the limit where we compute, say, let me embed this process into Penrose diagram. So let's say we have this process happening somewhere, and we look at it at Scri plus. So there is some retarded time. And we look at the change of the metric before and after. The result is that you find that delta h mu is given by 4g over r. And here you have sum final minus initial here you have final momenta so you carry some index I for some index j of initial momenta. And n is defined, here it's a 4 vector. N is defined as a null vector, which has 1, the first component, and the direction on the sphere where we observe the waves. So as usual, at plus we have a sphere. And if we look at some point on the sphere, it fixes some vector. And if you observe the memory in the direction of this vector, you find this formula. And if you forget about this factor, you can recognize that this is exactly the soft factor that appeared in the amplitudes discussion. I will explain it more. Why is it happening? But even though this formula was written in scattering amplitudes papers long time ago, and in the context of memory, appears in the paper by Braginski and Thorne in 1984. The connection between these two subjects was not noticed, even though the formulas, if you look at them, they're just identical. If you compare paper by Weinberg and their paper, they're just identical. And as soon as you realize this relation between soft theorems, or between the soft factor and the memory effect, you can generalize both considerations in many directions, as I will try to explain. This, well, even though I don't like so much this terminology, but let me call this consideration, say, a linear memory. So call it linear memory because what I did is I took some Einstein equations. I took Einstein equations, and then I consider perturbation on top of Minkowski space, and then, well, in general, we can take any source you like. If we have a computer, we can model some black hole merger or anything we like. But of course, Einstein theory is nonlinear, and in principle, we should be able to do the full nonlinear analysis. And notice that the character of this formula is has two striking features, I would say. So first, you see that if you put your detector somewhere on the sphere, that the memory here is a truly infrared effect, in a sense that to compute the memory at a given point on the sphere, you have to know the position of all the sources. So you have to, in a sense, you have to take care of the distribution of energy on the whole sphere. So that's an important fact. And the second point, which is important also to have in mind, and I think it's related to the fact when you do computation in, say, in perturbation theory, you encounter infrared divergences, and you have to go through, well, as you read in quantum field theory books, through these resummations, etc. Is and I will explain the connection with it. The second fact is that whenever you have some non-trivial scattering, which is, notice that if all the momenta in the initial state are equal to momenta in the final state, then this memory is 0. Which means that if there is no scattering, if just particles go through space-time, there is no memory. On the other hand, whenever there is some non-trivial scattering, this thing generically is non-zero. So the message we can learn from that is that for generic source we expect to have memory. First and second, it's infrared effect, which knows about the whole sphere. And well, for this simple case, it's given just by the soft factor. Well, as you learn, there is a relation between soft factors and BMS symmetries. And here I try to demonstrate to you that there is a relation so far between the memory and the soft factor. So one link we can now try to establish is what is the relation between say, gravitational memory and BMS symmetry. And that's what I will plan to do next. But let me first ask if you have any questions about the linear memory effect. We did something very, very simple in the first order in gravitational field, or if everything is clear. OK. Then let me switch to the, say, nonlinear analysis. Well, by nonlinear analysis, I mean the following setup. Imagine we have a Minkowski space, asymptotical Minkowski space. And again, that's what we usually do in real experiments. we come at some point in time, roughly at null infinity. In reality, we see it somewhere here at finite r, but let me ignore that. We come at some time u0, u initial, and then we observe for a while, and then we have some time u final. And in between, something can happen, hopefully. We're not just waiting. Some radiation comes in. So there is a black hole merger or something happening. Now, as you learned, but let me quickly remind you that when we describe physics close to null infinity, it's convenient to choose a so-called Bondi gauge, and in the Bondi gauge, the metric takes the form familiar form, and take you probably see this formula in every lecture, but my lecture is not exception in this regard. So the important point about this kind of transitions, and let me imagine that we start in some sort of stationary state, in some vacuum. So MB at U initial is some M initial, and MB at U final is some M final. Then, as you learned that in general, in this vacuum state, this vacuum state is not unique, and it's characterized by a so-called supertranslation. And under supertranslation, this CZZ takes the following form. And so this F, some supertranslation. Now the thing is that in principle this is a large diffeomorphism, and we can choose a frame where at the initial state we can do a gauge transformation where at the initial state F equal to 0. But as soon as we choose it at some point in time, the Einstein's equations fix for us F for all other times. So if you wish, if we choose, well, it's natural choice. When we come here to the initial state, we can consider CZZ to be 0. But then what the analysis of asymptotic infinity tells us, the basic lesson is that if you start with a 0 supertranslation, and then something happens, you will get a non-zero supertranslation. Yeah.
Quick question, sir. Is there a reason why there was no gravitational memory?
Well, yeah. So I tried to explain the actual signal. I think has a memory, but the detector does not, and this is signal for the detector. Yeah.
This is a bit going back to the linear.
Yeah.
So do these higher moments have anything to do with the subleading responsibility?
Yeah. Yeah, so one way to compute, so if you do Fourier transform of this, you'll just get these moments. But in general, well, when you're defining the moment, you can choose this u0 as you like. And so if you choose, say, u0 to 0 here, literally, they will be related to higher moments. But the problem is that, say, if you have when we compare this memory, you put your detector, and I put my detector, and we will agree on the memory. But here we will have to agree also the shift of u0 is by shift by a memory. It's the first thing which is annoying, and the second thing which is annoying is that is that here really you have to integrate over the whole time. It's not a boundary value of the function. So you have to know the shape. The first moment knows this knows only about the difference. But to get this, you really have to integrate well, or in other words, to compute this thing. So, but in principle, you can relate these higher soft modes to this kind of observables. I don't know if they're interesting in practice, or well, but probably one can compute them and compare. And I will talk about another way to measure this subleading factor, which does not have the supertranslation ambiguity in the second part, but one has to do some little tricks to get rid of this. And also, it also kind of more like a boundary effect. So there is a way I know how to do it for M1, but I don't know for M2 and higher moments how to do this. Other than that, in principle, one can try to imagine designing some kind of a good procedure, but it hasn't been done so far. Yes, so the basic consequence of this the Einstein equations that if you start with 0f and then something happening in space-time, then you get to non-zero f. So you get to transition to another vacuum. And to describe this vacuum, it's we can use, or to describe this transition, we can use Einstein equations. And so again, we start with, say, MB equal to M initial and CZZ equal to 0. And we end up with MB equal M final and CZZ non-zero. And then we can, there is some constraint from the fact that, well, again, from some other parts of Einstein equations that you may encounter in the previous lectures, that in these vacuum geometries, they have this property. So you can solve it as, again, CZZ equal to -2. And now to relate this f to what comes to null infinity, we just write we can write an Einstein equations for GUU, which takes the following form. And now the problems that I would like to solve is to find f which describes to transition to another vacuum using this equation. So it's a very simple problem. Okay, the solution is just inversion, if you wish, of this kernel. First we integrate this equation over U, and we use the boundary conditions and the fact that the space-time in vacuum, and in this way we get this equation. Again, what I did is I just integrated this equation over U, and then rewrote the change in delta MB as delta MB. Now we can plug this delta CCZ is Z final minus Z initial. So we'll get roughly this. And now we have to invert this kernel. Well, you can check. That's not hard exercise. That the answer is that the state of vacuum, the point on the sphere, is described by an integral over a sphere. With some kernel, which is an important thing. And here we have integral from initial time to final time over TUU plus delta B. So that's a formula, and the kernel, this kernel takes the following form. It has the following form. Where the relation between this sine and z is the following. Okay. Let's look at this formula, and the basic feature of this formula is the following: that similar to the discussion of our of the linear case, you can see that this vacuum transition has the property that, given some flux of energy, these are the particles arriving to null infinity, the kernel has support on the whole sphere. Let's say you compute the vacuum transition at point z. Then this function is non-zero on the whole sphere. So to compute the transition at the point z, you have to integrate over the whole sphere. Which means that generic signal will generate you a gravitational memory, which is related to the energy flux. And you can show that if you start with a space-time which start with some free massive particle, and say they end up also propagating far away in the final state, this delta MB is also, you can compute it, and it's something that we just did there. So actually this delta MB, for the case of black holes, if you start with initial black holes which are boosted, and then a final black holes, you will find that this delta MB will exactly of this type of the soft factor. But now, in the full nonlinear case, when we solve here, the analysis of Einstein equations was completely generic, and this TUU part has the contribution from the matter, but also it has a contribution from gravity waves itself. If you remember, this TUU has a piece which is a NZZ, and NZZ is related to a gravity wave. So now this formula has a feature that it takes care of all the nonlinearities. It's just exact. It knows about everything. It's a completely generic case. And I will explain now the relation to the memory effect, but you can already guess that by just similarities that one way to think about memory is exactly that memory, in a sense, is a super translation, the gravitational memory is related to supertranslation. And the fact that its analysis now is fully nonlinear, it deserved its own name in the literature. It's called nonlinear memory, and this formula of the sort was derived first in 1991 in a paper by Christodoulou. But this, well, and sometimes there is a division in the literature, what's called linear memory, if it's sorted by massive particle. If it's solved by gravity waves, it's called nonlinear. But if you say high energy, if you're a person who is coming from quantum field theory, and then say you look at the soft factor, for you all the particles are just the same. Gravity couples to everything. And so the basic point is that the energy flux causes this vacuum transition between vacua. Now, to really connect it to the memory, I will have to tell you a little bit about the behavior of geodesics in this space. So, well, first thing is you can consider. So, okay, now we have to agree what are our detectors. A simple way to a simple choice of detectors are so-called BMS detectors, even though it's very important that these detectors are not geodesic detectors, they're accelerated detectors. So each of the BMS detector carries a little rocket, which keeps it fixed according to with respect to some particularly chosen boundary frame. Or BMS detector is defined as a detector which stays as soon as you fix the gauge, and then the BMS detector stays at z equal bar equal to constant. That's the definition of it. And okay, the question how to realize it in practice, I don't know. But it's a convenient choice. So let me discuss it first. Then you can see that the form of the metric has a striking significance similarity with what we started today, which is the case of just planar wave, where we had a flat space, and then there is a correction, and the correction was in the bar components. And here, even though these are not geodesic observers, but they stay at z and z bar being fixed, and so you immediately conclude that the change of CZZ is exactly the change of the distance between the detectors, because well, you can rewrite it, say well, L plus delta L square. We will be working to linear order, so you write it, keep it delta L, and so the leading correction from this formula takes the form 1 over 2L. And then we just multiply by this part of the metric. And again, so what I'm imagining now is that we start with null infinity. There are two detectors. They start at some distance. There is some radiation coming. And then the distance between them changed. So this change in the distance to first order is given by, and notice that the important point is that we have to talk at some finite distance r naught now. We cannot go to infinity. This is a 1 over r effect. So the change in distance is this, plus times delta z square plus complex conjugate, where now I imagine that we choose a point on a sphere, and we choose two detectors, which are separated by some delta z. And if you want to relate, if you have a detector of some finite physical size, and you want to relate it to the separation on a sphere, it's not surprising that it's roughly L over R naught. So, well, indeed, this is just angular size of an object of the size L looked from the distance R naught. Well, now this delta CZZ we just computed, we can plug it in. And the basic result is that, well, you have an effect that the memory is just related to L over R naught. So it's a 1 over R naught effect. And then you have this kernel and this integral of TUU plus delta MB. So that's in this way, you can just see that the change in the vacuum, which is given by delta CZZ, or equivalently F, is, if you know that, you can compute the memory. And or equivalently, you can put it differently. You could have asked, OK, so we have a space-time. We can do large gauge transformations. What is the physical significance of those? How do we measure them? And the answer is that you can measure them through the gravitational memory effect. And as I will explain also next, the same you could have asked, OK, well, if you have a soft theorem, what is the significance, or how do you measure the soft photon? And the answer is that, well, soft photon will be related to the same transition. When do you usually have a break? Now or in 5 minutes? OK, let's do in 5 minutes. Just to finish this part of the talk, I will quickly tell you how do you get to the soft theorem. So relation to the soft theorem. Well, one thing you might so what do we do in quantum theory when we computing this thing? Well, we compute the expectation value of we take some state and we compute the expectation value of, say, CZZ or delta CZZ. So if you remember that this is so-called informal. It's if you're familiar with quantum field theory, this is so-called, well, Schwinger-Keldysh or in type of observable. But we can rewrite it as a sum over all final states. And it will be some final delta CZZ, some psi. And usually when we talk about some semi-classical process, which say we do, and let me talk about semi-classical process. Because notice, in principle, you can choose very quantum states with many superpositions of photons coming or particles coming from different directions, and then they will evolve into superpositions of states also, and then we really have to compute this in type of observable in quantum theory to compute the memory. But now imagine that you have some initial state, which is, say, a set of particles, which scatter into some final state. So this sum is really absent. You have some F star, which dominates the sum, if you wish. Well, then you get that this expectation is just given by some final delta CZZ initial over final initial. And since we are measuring delta CZZ far away, and this is just symmetric, and we can rewrite it as a, and now these are scattering amplitudes. Notice that scattering amplitudes are transitions. And delta CZZ is, if we do a Fourier transform, it's an insertion of a soft particle, because it's an integral over, well, it's integral over time of delta of C. Yeah, well, let me write it. Just. And this is just an insertion of a soft particle in the final state here. By the Fourier transform, if you wrote the composition in terms of the modes on some of the previous lectures, and then you know that by the soft theorem you can just this is related. And notice that this delta CZZ we measure at some point on the sphere, and there is also some point that labels a creation operator. So we have a ratio of two amplitudes with an insertion of a soft particle, and well, and this is given by exactly it's proportional to a soft factor. And this is what we got here. This is a soft factor. And this prefactor comes from the fact of how do you relate. Imagine you have a field somewhere on the sphere at Scri plus, integrated over U. How do you relate it to some creation operator? And there is this 1 over R factor. I don't know, have you discussed LSZ in the coordinate space? It's Lemon-Simanchik-Zimmermann. So this is this dictionary. In this way, we have established that well, there are three different, and notice also that the soft factor, it immediately emphasizes that it's completely universal effect. It does not care if the particle is massive or massless, if it's a graviton or not. So to this separation, which was natural from the point of view of maybe people who study gravitational theory in classical theory, and from the point of view of scattering amplitudes, it's very universal. And then indeed, this Christodoulou formula, when we consider the flux due to gravity waves here as being just set of some gravitons, we will just get a soft factor for gravitons. So this will becomes a soft factor. But generically, if we have some nonlinear merger of black holes, so we compute some pattern of gravity waves, then we will have to do this integral. And again, so, the maybe two things which I would like to emphasize from this discussion, apart from these relations that vacuum transitions you can measure using gravitational memory, and also they're related to insertions of soft photons, and also you can compute them by soft factors when you have a simple state, if you have a simple process with a few particles. An important, I think, point is that it is truly two things which I would like to emphasize. First, that it's truly infrared effect, by which I mean that to compute the memory at one point on the sphere, you really have to integrate over the whole sphere. And second point, which is very important, is that whenever you have a scattering, which is whenever you have a change in the flux or change in this quantity, you will get a non-zero memory. And And this is why, say, if you take scattering amplitudes and you start compute on top of some Fock space, you start compute loop diagrams, you'll have infrared divergences, because infrared divergence is telling you that you are not taking properly into account these infrared effects. And as far as I know, there is no, up to date, there is no really a good way to take care of all that in a systematic fashion. How to, maybe what is a right scattering matrix, which immediately is finite. Well, there are some constructions, but it seems that it's still an open question. So in here, I would make a break, 5 minutes. Yeah. Start or? Yeah. Now let me try to continue a little bit with the leading with this gravitational memory, and then I'll discuss so-called spin memory, which is related to subleading soft factor, and we'll say a couple of words about electromagnetic memory. But the idea will be always the same. That there is detectors, and the effect of large gauge transformation is non-trivial on them, and this is kind of memory effect, and then you relate them to some energy fluxes using soft theorems. One thing which I would like maybe to emphasize again is, remember we had this kernel in the integral, and it looked like that, roughly. So you can ask the following question. Imagine I have a detector, and it's in a desert, and the horse runs through the detector. Does it cause a lot of memory compared to some jet which goes very, very far in the galaxy? Or the answer is that you see that this kernel has a very, well, with the horse we have to discuss. This kernel is not peaked along the direction of observation. So if you consider theta equal to 0, the kernel is 0. But if you consider, say, theta equal pi over 2, or the whole point on a sphere at null infinity, it's of order 1. And now the energy which you produce when two black holes merge is gigantic compared to the energy that carried by a horse. So that's why this memory effect first really got contribution from this from all angles on the sphere, and then they also have this well, they big when the total energy flux is big, which is of order of, I don't know, solar masses and some in the mergers that was observed. Now, second is that I started well, introducing the detectors by saying that these are two bodies with some structure, carrying some structure. For example, they can carry a clock, and they can exchange. He can send a signal to his. So they first synchronize their clock, then something happens, then I send a signal to the other side, and then somebody stamps a time that he has, and it comes back to me, and then I can compare if this time is exactly, so how it agrees with time in the middle here. And if it's not equal to, then our clocks got desynchronized. Well, let's say the distance is not changing anymore. And what you do, if you do the computation for BMS observers, you can find that BMS observers, their clocks are just measured by U. So if you wish, you can, for BMS observers, you can think about their clock as being measured by U. And so if we have two observers with different Z, but it's same U, they synchronize their clocks. Then after the radiation passed through them, there is this term in the metric which looks like that, which I haven't written today for. And notice that this term is odd in z. So if you solve for say ds square for propagation of light, it will take a different and you plug here a Bondi gauge, and you solve for, say, it's going from z1 to z1 to z2 versus z2 to z1. This term will contribute with a different sign. And well, in this way you can show that the BMS observers, their clocks got desynchronized. On the other hand, there is this nice fact, which is useful to remember in just every discussion, is the following: that let's imagine now, instead of talking about this mysterious BMS observers, which we don't know how to realize in practice, we can talk about normal observers, which are simply free-falling bodies which follow geodesics. So for these free-falling bodies that follow geodesics, you can show that first it's a nice exercise to do to find geodesics in this Bondi gauge. Well, the answer is there for velocity takes this form. And here you have and here is complex conjugate of this. You see that compared to BMS observers, these geodesic observers, they drift in z direction. So if you compute the full velocity, you start with some fixed z, then they will start drifting in z direction. And to keep yourself at fixed z, you need a rocket. Now, there is this, if you want to discuss local experiments, there is this nice coordinate system, which is natural for local experiment. It's called Fermi normal coordinates. The construction of Fermi normal coordinates is very simple. You take some observer, some geodesic, say gamma of t, and then at every point you also shoot geodesics in the orthogonal direction, space-like geodesics. So this is time-like geodesic, space-like geodesics. And then you can introduce coordinate system in this way by choosing a basis. And the nice property of this Fermi normal coordinates is that the spacetime is manifestly flat, close to this observer. As you know, at every point locally you can choose Christoffel symbols to be 0. The Fermi normal coordinates is a system where if you compute Christoffel symbols along this curve, they're 0. And this is completely generic. It has nothing to do with flat space, with this asymptotic problem of memory or whatever. And so what you will have is that the metric there is this coordinate system where the metric takes the form, just Minkowski metric. And then you have corrections of order x squared, which come roughly, they take the form, say, well, it's very rough, unfortunately. You take x nu, x rho, the x mu, but you can find it in the books. So importantly is that the Riemann tensor, as it should, describes you the departure of a spacetime from flat, but The leading piece is just Minkowski space. And so you can compute, you can take this geodesic and compute the Fermi normal coordinates close to it, and compute the effect on somebody who moves nearby. And you will find again that the same displacement takes place that we discussed for BMS observers, that to leading order the displacement does not depend on geodesic versus BMS. But if you consider two nearby geodesic in general spacetime, you see that it's never possible to get the time delay which occur for BMS observers linear in separation. And the reason for that is roughly that because this correction is quadratic, there is a redshift which is responsible for this desynchronization, but this redshift is quadratic in x. Whereas if you will compute the geodesic, so you can find that this effect that we were discussing, it was linear in the displacement. So the generic point which I would like to make is that in every spacetime, in every situation, so the difference between geodesics observer and the BMS observer is that they both agree on the memory, but for some of them there is a desynchronization of the clocks, which is for BMS observer. But for geodesic observer, you can check that the linear order, there is no clock desynchronization. And the simple explanation is that actually there is also a similar construction for the. Well, here I consider a geodesic, but you can consider accelerated observer, and this is called also, you can look it up. It's called Fermi-Walker coordinates. Which will describe the metric seen by a person who accelerates. Again, he will see this, but the difference is that he will see a correction in the GTT, which is related to his acceleration. And that's exactly what's happening between difference between BMS observers and geodesics observers. You can see that the difference, the time desynchronization was related to the first derivative of z. The first derivative of z appears in the velocity, so if you want to set this to 0, you roughly have to accelerate with this. And then in the completely generic language, when you have acceleration, you can expect time desynchronization due to the usual time redshift. But maybe so two things that you can remember from this discussion is that first, for this BMS observers, there is an effect which is related to desynchronization of the clocks. But for geodesic observers, there is no. And moreover, if you remember how the supertranslation acts on the metric, it shifts u. If you remember, I don't know if you remember, but let me remind you that the supertranslation shifts u. So you could have thought that, well, maybe it just describes desynchronization. But as I try to explain, it really describes this motions on the sphere, this memory effect on this residual deformations on the sphere, and for geodesic observers. But really, it's not directly related. For them, there is no clock desynchronization. So if you could have thought that shifting u and supertranslating is dual to or describes desynchronization of the clocks, that's misleading. So that's the first thing regarding this story. And in generic story, you could have expected this on general grounds by thinking about this construction of specific coordinate systems which have even their own names. One related to geodesic observer, and second is related to accelerated observer. And then they have this interesting piece. Okay. So with this,
Even this observer will see the same memory.
yeah, it will say the same memory. Yeah, they will agree on the memory. So this is a leading order effect, which will they agree. Yeah. Now I would like to describe you. So this is, in a sense, this memory effect was known for many years, but now since as we learned about the connections to soft theorems, you could have wondered, okay, so there are new soft theorems that, I guess one of them you learned at the last lecture. Maybe there are new memories. And indeed, you can start talking about new memories inspired by that. And for example, the memory effect in electromagnetism, which is very simple. Even though electromagnetism is so old, I think it was not discussed before. So I don't know if one has to be proud about that, but just a fact. So, but next I would like to talk about this new memory related to subleading soft theorem. And here, okay, let me summarize this. What we have a leading soft theorem. So it was supertranslation, related to supertranslation. So there was deformation of the detector, this deformation of memory. And this deformation, well, I don't know why is it arrow? I just, and it's related to the energy flux, roughly to the energy flux through your detector, energy flux through the sphere. Now there is a similar story, which is we have a subleading soft theorem. We will have super rotations, so-called, which I assume you already learned. And there will be here some time delay, which I will describe. And it's related to the angular momentum flux. So that's the idea. To see how it works, let me again start with a metric in the Bondi gauge, but I will correct it. And the corrected metric takes the form. Yeah, you have it, so maybe you don't want to write it. And well, there is mass aspect as usual. And now we have the term we already had before. But we also have this new important piece, which looks like that. I don't know if you use the same convention, but let me stick to that one. It's called angular aspect, and there is a new equation of motion related to it, to this guy, which takes the form you already might, maybe you're already used to thinking always in these discussions about what is the soft particle, what are the hard particle effects in every formula. And this formula is not an exception. end it finally. So the derivative, again, as usual, the constraint takes the following form. The dynamics with respect to time, which is u, has this soft part. And then it has this hard part, which will be related to the angular momentum flux. So the idea will be, again, to use this equation to relate the response of the detector to flux of something else that we like to measure. Let me talk about the detectors. The detector here will be, and again, the idea, if you wish the goal, you could have asked, OK, why don't you wrote this formula for the moments. Why don't you use this formula? But this formula has this unpleasant feature that we have to integrate over time. Maybe one can do better and just make an experiment where you really just probe this this subleading piece. And also, people who are doing different experiments, they don't have to agree what is the origin of time for them, this u0 that was in the game. And the idea is to consider, again, we always think there is some piece of null infinity. Particles are coming. There is a sphere. We do the experiment locally on the sphere. And now the idea is that, well, let me draw this point on the sphere, so z0. To consider a ring, and we take two clocks, and we just send them, we synchronize them. First we synchronize. And second, we let them run along the ring in the opposite direction. Run in the opposite direction. This is similar to what's happening in the usual colliders, where particles are running. But the difference is that each of them here will carry a clock. And instead of colliding, they will compare their clocks. Again, maybe it's not the most practical setup, but why not? Now let me do the computation, which is very similar to what we did there, to compute this desynchronization. Well, it's actually just identical to it. So we have, imagine there is some point on the sphere. We can choose this z to be 0 for simplicity. So we have some z of phi, which is as L over R0, which is the size of the ring is L. And as I told you, that in practice we always do an experiment at finite distance. So this is R0. And the angular size is L over R0. And we have some phi here. But now the phi depends on u. So what this trajectory describes? It describes a particle which runs around the circle of fixed size in BMS coordinates, which is, and the dependence on time is controlled by phi of u. Now the equation we would like to solve is this. The square is equal to 0 for geodesics. And it will take the form which is, this simply comes from du square term. And this comes from dz bar term. And importantly, it has that term. Well, let me write it maybe fully. So there is the czz term plus complex conjugate, and there is a dz czz duz plus complex conjugate term. So this has to be equal to 0. Okay, well, as I tried to explain the difference, the qualitative difference between these two terms that we discussed about in the context of the usual memory, and this term that it's, when we flip u to minus u, these two are even and this is odd. And this is the source of the effect. So if you take and compute this geodesics and compute the difference the difference in time over one cycle, you will get that it's a contour integral. It's not necessarily actually a circle. It doesn't matter. So this is a, say, one turn. And if you want to write the formula which accumulates this, let's say we have radiation coming for a while. All this CZZs depends on u. So to get the formula for the whole thing, we just integrate over du from u initial to u final. And that's a delta u. Okay. So here's a proposal that it's nice to consider this loop and to run particle in both directions. And you can see that the desynchronization, which is, if you remember, it's related to BMS observers. Here we also fixed z, is controlled by this quantity. Now, the nice thing about this quantity is the following, that if you set CZZ to be d to z of phi, and you plug it in this formula, it's just a total differential and it's 0. So it's just a statement that if you inside, if you are, nothing is happening, the space-time is in the vacuum, then the delta u is not changing. That's very nice. Now the second part is, of course, to relate this quantity to the angular momentum flux, as I announced before. So where is the equation? I have it. Yeah. So to do that, we will need to use. Okay, I will have to. To use this equation. So let me write again here. So if CZZ is the second derivative, then delta u is 0. So to relate this quantity to the angular momentum flux, we will use again this equation, and you can show that using Stokes' theorem that it's a good exercise, that this quantity will be equal to this quantity. Well, I will go through it partly now. And then we can relate this desynchronization to the angular momentum flux. Okay, so what do? We consider we can consider the following. Well, if you remember, this is the part of the equation is this GUZ TUZ. So we can consider dz bar GUZ plus minus dz GUZ bar. And the important equation that one gets has the following form. dz bar dz3 czz is equal to imaginary part du dz bar and z plus dz bar tuz. Anyway, that's just follow from that equation. We had here a third derivative. We took one more. So and notice that here I took the minus sign, and because this term, if we differentiate it with respect to z bar, it will just cancel. So that's why MB cancels. Okay, so again, as before, we can use now some simple complex analysis theorem, and to invert this kernel and write partly invert this kernel and write a formula for delta U in terms of this quantity, and the answer is that delta U is equal to minus L imaginary part integral over the disk inside the disk It's a little bit ugly formula, but be with me. The meaning will be simple. Okay, that's the result. It has there are few important features. Well, first let me write again the here g is equal to simply log square theta over 2, and the sine square of theta over 2 is related to Okay, so this formula has several features that, apart from technical details, which are important. Again, you see that the kernel, first the kernel has support on the whole sphere, as before. Then the fact that you have this integral, so again, it's an very, well, it's an infrared effect. And the second thing is that this integral here over disk, which is surrounded by a contour C, And if you remember that on in the angular size of the circle was L over R, so this effect is L square over R square. So it's compared to the leading piece, it's suppressed by 1 over R. So I don't know if it was clear from my previous from our discussion of the leading memory, but the leading memory is 1 over R effect. This is 1 over R squared. And then this funny integral, you can let me write this. If we do the exercise with particles, as we did in the very beginning, where I wrote for you the stress tensor, you take again some particles, let's say massless particles, and compute the stress tensor far away, close to null infinity. You will get that TUZ for them is equal sum over particles, time when they arrive, and then here you get the point on the sphere where they arrive, and this is orbital angular momentum. And here you get the helicity part, which is the intrinsic angular momentum carried by the particle, which appears in quantum mechanics. And this bracket acts on a delta function on a sphere. Here there is a ZZ bar. Okay, so again, the basic story is the same, that you consider instead of the energy flux, you have an angular momentum flux. So this memory is called spin memory. It was discussed only recently, and one unpleasant feature about this, as you might have noticed, is that I consider it a ring of a finite size in the BMS coordinates. And I told you that in the original, for the original memory, it was this time shift effect was gone for geodesic observer. So one question is, which one can ask? Imagine we have well, as you know, that there is a LIGO now, which is on the Earth, and ELISA or ELISA, which is in the space. If we have a set of detectors, set of satellites, each of them is following geodesic. If they will observe this effect. So as far as I know, it was not, say, answered in the literature. So I'm not sure if they will observe this effect or not. Because otherwise, if it's some rigid ring of BMS observers, or let's say this is an LHC. No, LHCs, there are protons. Well, we can imagine that the proton has a phase which oscillates, so it's like a clock that it carries within. Can we observe the gravitational memory effect with LHC, for example? Again, one has to. LHC is not a BMS observer. They haven't built it properly. So, so we have to. Well, somebody have to understand that, I guess. It would be nice to understand this and clarify this. I think that's an open question regarding this spin memory. And the relation with, relation with the soft factor is again very similar. Let me just remind you that the soft factor that you learned in the previous lecture is given by this sum p k mu j nu lambda q lambda q dot pq. Okay. So lambda is a momentum of a soft particle, and it's gauge invariant. I remember the previous lecture ended with checking that it's gauge invariant. And the important point is that when you consider now a detector on a sphere, you just choose this q to be, say, some omega, the observation point on a sphere. And then you take where n is the point where your detector is. And then you can show, again, I can give you the references for the lecture. I don't know if it will be online or something, but you can check that. Again, if you plug this relation between the soft factor and this, and use the soft factor as we used for the original memory, you reproduce this formula with this just tensor and this delta u. So that's it just works very similar. Yeah.
Sorry, can you, instead of just using a circular ring, can you use any sort of loop that is enclosed?
Oh, yeah. Sorry, I have to emphasize that this C is any contour, actually. I just start with a loop, but it's any contour. This formula is true for any contour. And here's the disk, so if there is a loop, let me do it. Emphasize that it's not circular. And then it's the integral over dc. This.
And do you require sort of the disk to have a large L at all in all regions? Like, can I take a very elongated sort of oval?
I think you can do whatever you like, really, here. But the question is that, yeah. So here's this integral, if we roughly proportional to the area, if nothing depends on it. So.
I guess my question is, how big does R not have to be for this to make sense? Can we take a very, very small loop?
Well, R naught is, so if there is something happening far away in space, and here we observe on Earth, that's R naught, right? So making R naught small, or sorry, maybe I was confusing. So R naught is the distance from the, say, the distance event to the observer on Earth. Say, so this is R naught. So it's always very large. Yeah. Now, in the last 5 minutes that I have, yes, sir.
So typically, you will have, in any realistic process, you'll have both super translation memory and super rotation memory.
Right.
So, and you said the way you would distinguish is that the super translation one would be like a 1/r effect. So
Yeah.
it would be a stronger effect.
Yeah, it's stronger effect. Yeah.
Okay. So when I send out these things on some loop, I would have to worry about the fact that because of super translations, the shape of the loop might be.
Yeah. You have to worry about that. Yeah. So that's why it's not so clear. It's not so clear if how to do it in practice, because you have to control your loop with a great precision to keep it BMS. So the rockets which are on the loop, to keep it BMS, have to be very, very precise rockets, which are precise to 1/r order.
I have a very basic confusion.
Yeah.
Super translations and super rotations are independent.
Yes.
They're both spontaneously built.
If you wish.
So, what are the goldstone bosons for the super rotations?
Well, this dictionary, I think, is not completely well defined of Goldstone bosons and spontaneous symmetry breaking. I would say that, well, I think the useful thing to remember is roughly is that if you have a space-time, well, let's say you compute a charge, then the charge, well, let's say you have a space-time and you compute the super translation charge and super rotation charge. So the super translation charge is given by, say, it measures mb of this space-time, and the super-rotation charge will be given by czz of the space-time. So in terms of Goldstone bosons, I don't know. I think that probably any statement that can be made can be made without saying the word Goldstone boson. So that's one way to think about that. And second, I would say that like in space-time symmetries, we have many. Say if we have a crystal with phonons, many symmetries are broken. But in space-time symmetries, the number of bosons is not equal to number of space-time symmetry broken generators. So one way to say that it's a space-time symmetry that is broken. So it would be maybe nice to. So there is a symmetry about number of generators that is being broken and number of Goldstone bosons, which is proven in quantum field theory for space-time symmetries or not. There is no such theorem as far as I know here, and I guess if there is one, that would be nice. It would be one way to put this picture of a Goldstone boson to a more solid ground to count how many of them we have. Well, I would expect that the czz is what we have, and that's it. So, but oh well, it's all very confusing. At least I find it, the discussion to be quite preliminary at the moment. Okay, let me just say a couple of words about electromagnetic memory. So let me write one equation and say just some words. So remember the equations of motions are this. So choose let's write for the component nu being u. So in the far away, the equation takes a form. And here, okay, so again, this will be a soft part. This will be a hard part. This is related to, say, flux of the charge. This is related to a radial electric field. All this memory formulas is relate the soft part to the hard part. You can integrate this with respect to u. And now, recalling that this is related to this large gauge transformation, then to talk about electromagnetic memory, you have to specify how do you measure the phase. So one way to measure the phase is the following. Imagine you have an electron, and you act with a gauge transformation on it, so you get a phase. So there's a setup for the gravity memory, for the electromagnetic memory can be the following. You take a bomb, you put it inside a sphere, you put electrons on the sphere, and then you control their phase. So you let the bomb explode, things are going away. And using this equation, you can show that the charge flux and the radial electric field carried will be imprinted in the phases of these electrons. And then if you can re-interfere them, interfere the electrons, then you can observe this change in phase. This is called electromagnetic memory. Or you can consider some superconductors, connect them with wires, and the superconductors have this phase, and this phase is transformed under this transformation, and so you can also do that. But the basic point, your detector has to be sensitive to the phase. So there is this just electrons interference or you can consider some superconductor. You can say this was, yeah, but the basic idea is again the same. And notice that to measure the electromagnetic memory is, interestingly, it's harder than to measure the gravitational memory, because to measure the phase of a particle, it's a quantum measurement. That's an interesting thing about this. And let me conclude also that the memory that we discussed and its relation to soft theorems and symmetries, the memory was always described by change in something. We always started with some set of calibrated detectors. The word calibrated is extremely important here. We calibrated them, and then we look at the change. For example, if you give me an electron and you ask what is its phase, this question is meaningless because I can choose it as I like, unless there is a God-given prescription to call that electron with the zero phase. Then I go compare with that phase, and then I know my phase. So similarly, if we go to the middle of the galaxy and they ask what is the supertranslation of this black hole, I think this question can only be answered if we know that there was some pre-given structure of the space-time. Well, this question I wouldn't go much into, but let me emphasize again that memories always relate transitions in the vacua to some fluxes. Thank you. Sorry for that. Thank you. That's it.